Chapter 8.4, Volume and Surface Area. So here we're going to take a step up in dimensions. We're going to look at three-dimensional figures now. So first, we need to talk about solid geometry. Solid geometry is the study of three-dimensional solid figures, also called space figures. The volume is sort of like the area was for our two-dimensional figures. It is the measure of the inside of our space figure, or our shape in this case. So it is the measure of the capacity of a 3D figure. It's the amount of material you can put inside that 3D figure. So just like area was two-dimensional units, perimeter was one-dimensional units, volume is now three-dimensional units, or cubic units, such as cubic feet or cubic meters. Then the surface area is the sum of the areas of each surface on the 3D figure, the surface being the outer faces of the figure. So here on this box I have drawn, this would be a surface, a surface, a surface. One over here, one in the back here, one on the bottom. There's 6 faces, which we can see reflected over here. Each of those rectangles added together, each area of each of those rectangles added together gets us the surface area of the shape. Now, because this is just a sum of areas, we are adding up two-dimensional measurements. Adding them means we just end up with another two-dimensional measurement. So it is measured in square units, such as, once again, square feet or square meters. In the same way that the perimeter was just adding up side lengths, the surface area is now adding up face areas. So here we have a number of common volume and surface area formulas. If you take a look at the formula sheet for the exam, you'll see that some of these will be given to you. So please familiarize yourself with them, but also take a look at which ones you'll be given. So first we have the rectangular solid. So the volume of the rectangular solid is length times width times height. Just like the area of a rectangle is length times width, we've now just added on another dimension here, the height dimension. Because essentially, if we have our area right here, and it's each of these units, then we add a new dimension. It's just how many cubes do I make by adding in this new dimension here, right? How many cubes am I making throughout? So that's how we get a volume, is cubic units. So we need 3 dimensions multiplied together, length, width, height. The area of this base multiplied upward by the height, how much gets us our volume. The surface area, on the other hand, is made up of these 6 rectangles, just like in the picture on the previous slide. So we get 2 length width, because this bottom and this top are the length times width. 2 width height, this side and this side are the width times height. And 2 length height, this front and then the back part, are the length times height rectangles. So we just get 2 of each of these rectangle areas, adding them all together to get the total surface area. Now the cube is again just like a square, but now we are expanding it one more dimension. So instead of s squared, we get a volume of s cubed now. The surface area, all sides are the same, right? All side lengths, everything is all s's. So we get 6s squared as our surface area because the front is an s squared, it's a square, and there are 6 of them to make the total surface area. A cylinder is sort of like taking a circle and stretching it up through space. So we need the area of a circle right here, pi r squared, which is the area of this circle right here, multiplied up through space is multiplied by the height. Just like the area of this rectangle was multiplied up through space by the height. Same basic principle here. The surface area of the cylinder, essentially we want to think about if you have a can, right? A can with a label on it. When I unfurl the label from that can, it looks like a rectangle. So the surface area of a cylinder comes from adding up the rectangle that makes up the outer piece of the can unfurled, plus these two circles, top and bottom. So 2 pi r squared is the two circles. The rectangle is length times height, but the length is going to be the circumference of this circle. So this is the length times height of the rectangle that makes the label on the can. So 2 pi r h plus 2 pi r squared is what we end up with that way. Now the cone is a little bit harder to sort of visualize, but essentially the cone is 1/3 of a cylinder. So it's 1/3 pi r squared h. The surface area, we're not really going to get into why it is what it is, but it is the most complicated of all of them. So we get the pi r squared from the base circle once again right here, but to get this sort of taking that, what it turns out to be is sort of more circular than the rectangle that the cylinder was made from. So we end up with pi r times the square root of r squared plus h squared. Finally, the sphere is technically like 2/3 of a cylinder. But the fact that the height would be 2 r's, we can get into the algebra of how this works out, but we end up with a volume of 4/3 pi r cubed, which is equal to 2/3 of pi r squared h, where h is just equal to 2r. So the surface area is 4 pi r squared. Again, we're not really going to get into exactly why that is, but if you're curious about that, that's something you can absolutely ask me about. Now let's get to some examples of putting these equations into practice. So if we want to find the volume and surface area of the given three-dimensional figure, here we have, what type of figure is it? Well, it is a rectangular solid, which means we have the following formulas. Volume is length times width times height. Surface area is 2LW plus 2WH plus 2LH. All we now need to do is identify what L, W, and H are. Does it matter which is which? No, it doesn't. There's some convention that height is usually, upward, but length and width, you may generally go for length being this side, width being that one, but sometimes we call that depth instead of width. It doesn't really matter which is which because it's all going to be multiplied together anyway. So I'm going to call the height 5, the length 10, and the width 2, though. So 10 times 2 times 5 is then 100. Now notice 100 feet cubed, because it is feet times feet times feet, or feet cubed. The surface area is then 2 times length width, which is 10 times 2, 2 times 2 times 5, 2 times 10 times 5, and add all that together. 40 plus 20 plus 100, which is 160 square feet. Notice it's square feet this time because each of these only has 2 dimensions multiplied. Length, width, 2 dimensions. Feet times feet is feet squared. Adding in more feet squared, more feet squared. We're never getting to a third dimension, so it stays as feet squared like any other area would be. Next, let's try this with a cylinder. So in this case, we have the volume of a cylinder is pi r squared h. The surface area is 2 pi r h plus 2 pi r squared. Then we want to identify which is the radius and which is the height. So the radius is, of course, the part of the circle from the center to one of the sides. So that is our 3 inches. And the height is the height of the cylinder. So that gives us radius 3, height 7, which we can then plug into our equations. Pi times r squared, so 3 squared, times height, 7. Remember that we square just the 3, so we get pi times 9 times 7, which ends up being 63 pi, which, putting it into your calculator, will give you 197.92 cubic inches because we're talking about a volume. For surface area, we then do a very similar thing. 2 pi times 3 times 7 plus 2 pi times 3 squared. Again, remembering that we square the 3 alone, so that'll become 9. 9 times 2 is 18, so we have 18 pi, and then 3 times 7 times 2 is 42 pi. Adding that together, we have a total of 60 pi's, because 42 plus 18 equals 60. So there's 60 pi's, they're like terms, which we can then plug into our calculator to get 188.50 square inches. Because once again, it is still a surface area. There's only 2 dimensions being multiplied together. R squared, RH. 2 dimensions being multiplied together. Even if we end up adding them, it's still square inches plus square inches. Now let's try it with, what is this one? A cone. And we already know what the volume and surface area for cones are, even though, once again, this is one of the more difficult ones. The volume is 1/3 of a cylinder, so 1/3 pi r squared h. The surface area is pi r squared plus pi r times the square root of r squared plus h squared. So that one's going to take a little bit of effort to figure out, but let's start by identifying what is the radius and the height here. So just like with the cylinder, the radius is half the length across the circle, half the diameter, and the height is just the distance from the circle down to the floor. That's the 7 inches. Then we plug that into our volume equation, 1/3 pi times 9 times 7. It's even the same numbers as before. So we get 9 times 7 divided by 3, which will end up being 21 pi, right? 9 times 7 over 3 is 21, which, plugging into our calculator, will give us approximately 65.97 cubic inches. Our surface area will plug in just the same, but now we need to sort of think out, how does this simplify? So, of course, our 3 squared will become 9, so this will be 9 pi. And we have 3 pi, but this square root, do not square root the 3 and the 7 and pretend like those squares didn't matter. Why would we write it like this if I just meant r plus h? I don't mean just r plus h. That's not how square roots work. You cannot distribute square roots over addition. Please don't do it. We need to actually add these together. 9 plus 49 is the square root of 58. So this square root of 58 is not the same thing as 3 plus 7. Trust me, you can plug it in your calculator to check, but I promise you it's not the same thing as just adding 3 plus 7. So, we now plug this into your calculator because the square root of 58 is not a nice number, and we will get 9 pi plus 3 times pi times square root of 58 is approximately 100.05 square inches. And again, I really do implore you to try this in your calculator to make sure you know how your calculator works and how to plug things like this into it, because it can be kind of tricky. So practice this on your own. Next, we're going to talk about just some more definitions of polyhedra. So a polyhedron, whose plural is polyhedra, is a closed surface formed by the union of polygonal regions. So if we're putting a bunch of polygons together, we get polyhedra. We've seen several polyhedra already. A rectangular solid is an example of a polyhedron. But, for example, a cylinder or a cone or a sphere, those are not polyhedra because they are not made up of just polygons. They have circles involved, and circles are not polygons. So, when we have a polyhedra, just like with a polygon, we have some specific parts that make them up. We have vertices, we have edges, and now we have faces. So faces are each of the sides of our polyhedron. Then the edges are just the literal edges of the three-dimensional figure, and the vertices are the points that make up where the edges meet or where the faces meet. We actually get this sort of nifty formula called Euler's polyhedron formula. Euler's formula states that the number of vertices minus the number of edges plus the number of faces should always equal 2 for any polyhedron, or in fact any three-dimensional shape, but we're not really going to get into applying this to not polyhedron. So let's put this to practice here. If I take this triangular polyhedra, right, or polyhedron, we have how many vertices? Well, there's 1, 2, 3, 4, so 4 vertices. How many edges? 1, 2, 3, 4, 5, 6. And how many faces? 1, 2, 3, and 4 is the bottom one. So we get 4 minus 6, which is now negative 2, plus 4, which is positive 2. And see, it works. We can do this with any of these, right? I have, for my cube, the number of vertices is 1, 2, 3, 4, 5, 6, 7, 8. The number of edges is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And the number of faces is 6. When I add all this together, 8 minus 12 is negative 4, plus 6 is in fact 2. Checks out. Try it with the other two. See that this will work. A prism is a special type of polyhedron whose bases are congruent polygons and whose sides are parallelograms. So again, we've already seen an example of a prism. The rectangular solid is also known as a rectangular prism. These parallelogram regions are called the lateral faces of the prism. If all the lateral faces are rectangles, the prism is said to be a right prism. So here we have examples of right prisms, which are the ones we are typically going to talk about in this class. So here we have a triangular prism, specifically a right triangular prism. We have a square prism, but it's just a cube. Square prism is the same thing as a cube. We have a hexagonal prism. And a trapezoidal prism. Now notice that the area, or the volume, is equal to the area of the base times the height. As I was sort of hinting at before when we looked at those volume formula, we take this area and then we multiply upward. Like this is the height. Once we have this area, we're layering it on top of each other for the height amount of space. Like that's what's really happening. So when you have a prism, it makes it very easy to find the volume because it's a very regular type of formula. In the same way that we found the volume of the cylinder works this way as well, though it is not technically a prism. Now, let's apply our new knowledge of prisms. So Frank's fish tank is in the shape of a hexagonal prism. We're going to use the dimensions shown in the figure and the fact that 1 gallon is 231 cubic inches to answer the question. So first, determine the volume of the tank in cubic inches. So to do that, we want to think, this is what type of solid? Well, it is a prism, specifically a right prism, with a base of a hexagon. So we know that the volume is the base times height, but we don't know the area of a hexagon. We were never given a formula for the area of a hexagon. However, we were given the formula for the area of trapezoids, and this hexagon is made up of 2 trapezoids. So we can find the base by finding the area of each individual trapezoid. Remember that the area of the trapezoid is 1/2 base 1 plus base 2 times the height. In this case, we have base 1 is 16 across, and then base 2 is 8 across, and the height is 8. So together we get the base, capital B base this time, of the hexagonal prism is 2 times 8 plus 16, again that's this plus this, divided by 2 times the height of one of the trapezoids, and there are 2 of them, so we get the whole hexagon. So together, this is going to be 192. Then we multiply by the height of the entire shape, which is this 24 right here. The 192 times 24, and then what's our unit? Our unit is cubic inches. So 4,608 cubic inches makes up our entire volume. Now to determine the volume of the tank in gallons, we need to remember we have a proportion. So 1 gallon is 231 cubic inches. So we can make a proportion once again and say, well, X gallons is 4,608 cubic inches. When we know that 1 gallon is 231 cubic inches. Do our cross multiplication to get that X times 231 equals 4,608. Divide both sides by 231, and we end up with 4,608 divided by 231, which is approximately 19.95 gallons. Once again, you may not have to do the proportion if you can think this one out without doing it. That's okay as well, but I think the proportion can really help guide you if you're unsure on working with units like this. So in the end, we end up with a number of gallons. The units make sense, and that approximately makes sense with our sort of real-world knowledge. So that's not an insane number of gallons to have for a fish tank. Our last type of three-dimensional solid we're going to look at is a pyramid. So a pyramid is a polyhedron with one base, all but one face intersect at a common vertex. So again, it's like we take a prism, and instead of pulling the base upward to give us the height, we are pulling the base upward but squeezing it together to a single point, right? So just like how the cone is like a third of a cylinder, we have all these other types of prisms that are thirds of, all these pyramids are like 1/3 of their prism counterpart. So it's 1/3 times the base times the height is the area of the pyramid. So here we have, again, this would be a triangular pyramid on the left, a square pyramid, a hexagonal pyramid, I guess this is a rectangle. It doesn't really look exactly perfect here, but we'll call this a rectangular pyramid on the right side. So they're always named by whatever their base is, just like the prisms were. So to find the volume of any given pyramid, we start by finding the area of the base. So what type of base does this pyramid have? Well, it's 5 meters by 5 meters, which means it's not just any rectangle, it is in fact a square. So the area is 5 squared, which is 25 meters squared. The volume is 1/3 times that base of 25 times the height of 6 meters. So 1/3 times 25 times 6, which equals 50 meters cubed. Again, remember that we are talking about volume. We have multiplied together 3 units, even though three dimensions, even though it looks like 2, there's secretly 2 here already, so it'll be an area times another dimension to get us up into cubic units. The final thing we're going to talk about is simply converting between units. So we already saw doing this with the gallons to gallons and cubic inches, but we can do this with a lot of other types of units as well. And there's more than one way to do this. We can do it pictorially, we can do it just sort of thinking out exactly how things are related, or we can create our proportions. So if I want to convert 1 cubic yard into cubic feet, I first need to know how yards are related to feet. So 1 yard is 3 feet. And here I have in a picture 1 yard split up into 3 by 1 yard split up into 3 by 1 yard split up into 3. So in other words, a cubic yard split up into the 3 feet that each yard is made up into. So what does that mean? Well, it means that 1 cubic yard we can find using a volume formula. It is 3 feet times 3 feet times 3 feet, length times width times height. So that gives us 27 cubic feet. We can also, again, have created a proportion to figure this out, that 1 yard over 3 feet, but we need to cube both, and really what we're doing is we're cubing the number 3. Like, that's how the proportion works out. It's not as one-to-one as proportions previously were, so in fact drawing it out is probably your best bet in a problem like this. So if we wanted to convert 5.7 cubic yards to cubic feet, now is where the proportion is going to be a little bit easier to work with, because we already know the relationship between 1 cubic yard and cubic feet. So we can say, well, 1 cubic yard is 27 cubic feet, and we want to know what 5.7 cubic yards is, how many cubic feet that is, so we can cross multiply again. So x is equal to 27 times 5.7, which is 153.9 cubic feet. Similarly, if I wanted to convert a number of cubic feet into cubic yards, I would do the same thing. I'd set up a very similar proportion, but now I'd have the x up here and the number, this number, right here. So we would end up with 843.75 equals 27x. So 843.75 equals 27x. Then we divide both sides by 27 to get x is equal to 843.75 divided by 27, or 31.75 cubic yards. We can do this with all kinds of units. This is basically what is called unit analysis. Using your units to help you solve problems like this is extremely important. Please think about your units anytime you're faced with a word problem. It can really help guide you towards your answer.